Welcome this evening to our webinar, first webinar in the Eco Retrofit for Householders series on understanding retrofit. I'm delighted to have Marion Lloyd-Jones of the Retrofit Hub as our expert speaker this evening. And I'd just like to say that this is funded by Energy Redress, and we're grateful for that. Hang on, the slides aren't moving forward. So for the first few minutes, first 10 minutes, I'm just going to say a little bit about CAFs and by way of introduction. Then I'll hand over to Marion, who will talk for 40 minutes about understanding retrofit. And then we'll have 30 minutes for Q&A session, and at the end, a poll, another poll, and a bit about the future events. So at Cumbria Action for Sustainability, for those who don't know us, our overall vision is a zero carbon Cumbria, and we do lots of different work within that for on all sorts of different fronts. So do have a look at the CAF's website, and that's where you can find out all about what we do. The energy side of things is just a small part of it. And just a quick plug for our Christmas gifts. So if you want to see what gift cards we've got, that also gives you a sense of the different projects that we run within CAFs, and you can give people a gift card as a present. So on to CAF's energy services. We have a range of free services and paid for services. So the free one's called to Cozy Homes, and I'll say a bit more about that in a moment, plus also courses and webinars like this one. And we have paid for services, starting with a free retrofit consultation by phone and a quote. For those who want a full home house energy model, our home retrofit planner carries out that model and a report. And then we have also got a pilot of new services that follow on from that through your retrofit journey. So Cold to Cozy Homes is a range of different options for help, a phone call, a home visit by an advisor, and a range of common sense and often cheap and easy energy saving measures to make. But now it does include retrofit advice and information about the government schemes that can help with retrofit measures. On the paid for services side, our home retrofit planner is an in-depth model of models the heat loss from your home. It calculates your carbon footprint and looks at everything that you're thinking of doing. Looks at your priorities of comfort, health, indoor air quality, lower carbon, whatever it is, and produces a report that is specific to you and your home. And then the further services help you through to the design stage and on to finding installers. And some of you will be at the webinar because you've heard about our Retrofit Made Easy events that we've been running in the autumn, and we'll be doing more in-person events in January and February 24 in those communities where we've started working already. So those communities, we've got 3 thermal camera surveys being done by our community volunteers, and you've got a list of the communities that are doing that there. And if you're interested in that, you can go onto the CAF's website and we'll send more information out afterwards anyway. The other project that we're running and have been running for a while is Solar Made Easy, and that enables householders to access independent advice and get quotes from 2 local vetted installers. So that's running in different communities, but also across the whole of Cumbria. You can just contact the Solar Made Easy on the CAF's, via the CAF's website, and join that scheme. Now, I'm really happy to introduce Marion Lloyd-Jones, who works at the Retrofit Hub in Manchester, helping homeowners to plan and actually complete their retrofit projects. And Marion also delivers training like this webinar today, and also training to builders in the construction industry. Marion is a retrofit coordinator and has a postgraduate diploma from the Centre for Alternative Technology. And Marion it's very exciting because Marion was working for People Powered Retrofit, but now with Retrofit Hub, she's actually out there working with a team of people who are doing retrofits, and I think that's incredibly exciting. So yeah, rolls her sleeves up, gets her hands dirty. So Marion's talking about this not just in theory, but from first-hand experience. So over to you, Marion. I'll just stop sharing.
Okay. Hello, everybody. I'm going to attempt to seamlessly share this presentation. Have we got it?
Yes,
Marvelous. Okay,
fantastic. Thank you.
brilliant. Right, let's have a go. So this is what we're going to cover. Um, this evening we're going to look at we're going to concentrate on the whole house approach, and then we're going to delve into heat transfer, how heat is lost from our buildings, looking at that combination of heat and air movement, and then look at moisture and why moisture is such a big issue. Apologies, I'm going to be looking all over the place because I've got the slides on the screen, I've got speaker notes on a phone, and I've got some notes as well. So I am in this, but I will be looking all over the place. So we'll start off. Yeah. Tina has given me a lovely introduction, and it is fantastic. And I do now work very closely with a team of fantastic contractors who are on site. We've currently got 3 projects running concurrently, various scales of projects, from sort of one-off measures. We've got we've just finished a floor insulation job, we've got a loft insulation job going, but we've also got a couple of jobs that are a combination of high quality triple glazed windows and doors with internal or external wall insulation at the same time, and an MVHR system that's gone in as well. We also do jobs. We're essentially like a small family construction company. So a lot of the jobs that we do will also include some kind of remodeling or renovation at the same time. But we only take on jobs that also have an energy efficiency retrofit angle to them. We don't just do any old building work. We're only interested in retrofit work. It'd be really lovely to know a little bit about who we've got in. So if you can pop in, let me know in the chat. A bit about who you are. I'm just generally interested. Who have we got? Are we people who have got projects going on, or people looking to do a project? So do please chat to me. I want to know about you. People powered retrofit. So people powered retrofit have put these slides together and are running the webinar series with CAFs. PPR are a project based in, well, an organisation now based in Manchester, who run a householder service. So taking householder clients all the way through from advice at the beginning, through a retrofit assessment process, then a design process where design is required, and then help with tendering with contractors, and then do evaluation work at the end. So they will do a hand-holding service all the way through, as well as doing contributing to retrofit research along the way. Essentially, they're a one-stop shop for retrofit covering Greater Manchester, but also working to replicate their process with other community energy groups. The idea that people who are taking an area-based approach. So people powered retrofit know a lot about the housing types in Manchester. That's where their expertise is, but also replicating the service model in other areas, CAFs being one of the organisations that they're replicating with. And also working with CSE, the Centre for Sustainable Energy, down in Bristol, and Devon Council as well. And they've got a couple more replication projects on the way. So the whole house approach, let's get stuck in. So what is it? Why is it important? So houses are, we take a systems thinking approach. So a house is a system made up of lots of different elements. So it has the fabric heat loss, the fabric being the physical bits of the building, the walls, the floors, the roofs, the windows, the doors. And that we lose heat through them. But there's also a ventilation system, or there should be a ventilation system. So this is all about extracting air that we don't want anymore, and bringing in fresh air. So this is another system piled on top there. There'll also be a heating system, because we've got to combat this heat loss that we're getting through the fabric and from ventilation losses. We need to add some heat so that we're not cold. We also have lighting and appliances. We want to be able to see what we're doing, and we need some kind of entertainment and appliances. We've got, TVs, computers, cookers, fridges, all these things we plug in, essentially. And then people. So all of this we can sort of predict. We can predict how the building is going to lose heat, what heat we're going to need to put in. To some degree, we can make an assumption about lighting and appliances, and that's all. We can make calculations about that, and then it gets really complicated when we add people, because people do things differently depending on where they are, who they are, how many of them there are. But they're also adding to the system. They're adding heat from their bodies, and they're also adding lots of moisture through their activities. And all of these systems interact with each other. They're not in isolation. There's lots of interactions, which complicates our predictions. Fab. Okay. George, I can see your question in the Q&A, just so you know. So why do we take this whole house approach? So this whole house approach acknowledges that how these houses are these really complex systems. But we understand really well how these systems work and how they interact. And the whole house approach allows us to take a really context specific and a risk management approach. A lot of very clever people have done a lot of brilliant research about the risks involved in retrofitting our buildings, and we can learn so much from them. And we can make sure that we consider all of these risks when we take on a project. It means that we can be aware of any potential unintended consequences. So if we do some air tightness work over here, are we going to introduce a moisture risk over here? We can predict that. And it also means that we can make sure that any new measures, so any insulation or ventilation measures that we are introducing to the building, we can make sure that they're really well considered, they're really well designed, they're really well installed, which is very important. And crucially, that they are understood by the resident. We don't want to install stuff that people don't know how to use. It makes them useless. This is a really useful tool I'd like to introduce. This is from the Sustainable Traditional Buildings Alliance. This is their retrofit wheel. Essentially what it does is they've looked at all the research, and they have this wheel where you can select what you're planning on doing, and it will show you the interactions between systems and measures. I would recommend looking it up. If you were to just Google STBA, I think they call it the Responsible Retrofit Wheel. Now, we take a whole house approach, and that means we can then make a plan. What do we mean by making a plan? Well, we need to get from here to there. How do we do that? With a retrofit project, it would be lovely to say that everybody does it all in one go, but that's just not the case. As in general, a lot of the projects that we do at the Retrofit Hub, people will plan as a whole house project, but in reality, it gets delivered in packages of work. This link down the bottom is from Eurofit, which is the Passive House Institute's step-by-step retrofit guide using passive house components. It's quite interesting if you're to have a look at how we might go from here to there and make a plan. It's very important that we do make a plan so that we make sure that we don't cause any of these unintended consequences that we do know about. So what might inform that plan? Well, we like to talk about a fabric first approach. What does that mean? Well, it basically takes into account this energy hierarchy, because it shows this is the most straightforward, the most predictable way of getting from here to there, reducing our energy needs in our homes. So the first step, the most important step, the fabric first step, is to reduce the space heating demand for that home. What do we mean by that? Well, if we focus on fabric energy efficiency, which is a fancy word for improving the fabric of the building. So we're looking at improving the insulation, improving the air tightness, and we'll come on more onto air tightness in a bit, and adding things like triple glazed windows. What we're doing is we want to make sure that that building is not losing the heat. So that means we don't have to put as much heat in with our heating system to be able to maintain a nice, stable, comfortable indoor temperature. I always say that the cleanest, greenest, cheapest energy is the energy that we don't need to buy. Okay. And we do that by reducing the space heating demand, less energy. The energy that we do then use, we want to use more efficiently. So we want to make sure that our heating system runs really efficiently. It's correctly sized. We've got radiators in the right place. It's a modern heating system where we're getting as much energy out of it as possible. Things like old boilers are sort of 70, 80, the really old ones, 70, 80% efficient. Newer boilers, 95, 96% efficient. Heat pumps, 200, 300, 400% efficient. So, really efficient heating systems we can have now. Really efficient lighting, lighting these days, LEDs, so much more efficient than your old incandescent bulbs. And we can get really efficient ventilation systems as well. And then after that, we want to make sure that energy that we're going to use really efficiently, we want to supply it from renewable sources. We want to make sure that it's the lowest carbon energy we can get. We're really good at decarbonising energy in the UK. So we're getting much better at this. And if we can supply some of that energy and that renewable energy on site, brilliant. Solar panels on roofs, a fantastic way. But I would recommend you doing that fabric work first. You definitely don't want to be dealing with having to replace a roof that's already got solar panels on. That is a bit of a kerfuffle, shall we say. So why do we want to do it this way? Well, if we've reduced the space heating demand, we can make sure that our building services, so our heating system, our ventilation system, more effective. We can also design for lower maintenance. If we make really sensible choices in our retrofit measures, it actually reduces the maintenance needed on a building. If we externally insulate, for example, we don't have to worry about repointing on a regular basis. If we install really high quality windows, we can make sure that we don't need to do so much maintenance on those windows. And this sort of runs through a lot of the measures that we can install. We have really reduced our ongoing running costs. We need less energy. We're much less sensitive to fluctuations in the energy markets. We can improve, we can have better living conditions, we can have really nice indoor air quality, we can have nice, warm, comfortable homes. Our homes are making us poorly at the moment. We spend 90% plus of our time indoors. We should have really nice indoor environments. Also, working this way, we can really reduce fuel poverty. If we're reducing the amount that we need to spend on our energy bills, then people, like I said, they're less sensitive to shocks in the energy market. They're not spending as much of their income on energy. Our homes are future-proofed. Not only are we going to deal better with colder winters, if we plan properly and do a really good job of installing these measures, we're actually going to be better for increased temperatures going forwards. We get a nice, more stable temperature all the year round. So we're really future-proofing our properties, whatever climate change has in store for us. And if we reduce our energy demand, it actually makes it much easier as a country to meet our CO2 reductions targets, because we can really concentrate on decarbonising the electricity grid. That is, at a grid level, is much easier than trying to deal with lots of individual households on gas or oil heating. If it's electrified, we can decarbonise that at a greater scale. But it's not that easy. We have a lot of different houses across the UK. There's a big difference in building types depending on how old buildings are. So this graph separates houses by building age. There's lots of different ways we split buildings up, but generally we say sort of pre-1919, that's your for us in Manchester, that's generally your red brick solid wall properties. That would also cover a lot of your stone built buildings. And then we hit sort of the interwar years, 1919, 1944. That's a lot of that is your early cavity walls, a lot of the buildings that were put up in those interwar years. And then after here, we tend to see we see a big there's a lot more different bands after here, basically, and a lot of these are tied to buildings regulations, which didn't start mentioning energy until 1965. That's when we first had targets for insulation in properties. And what we would hope to see is that buildings built from then on, as there's been improvements in the targets from buildings regs for insulation and airtightness, they should be better buildings from that point on. I won't go into why that's probably not the case, unfortunately. But this is why we break things up. But it's important to understand there is a real range. Also, we don't build many houses anymore. So why is this important, the age of the house? Well, how fundamentally older and newer buildings are built differently. Older houses, so especially those pre-1919, that big chunk at the beginning, and the interwar houses, they were built to be heated by coal fires or wood fires. Basically, you wouldn't be expect to be warm unless you were sitting in front of the fire. They were made from traditional materials, so we call them breathable materials. I'll come on to that in a bit. What do I actually mean by breathable? But the important thing is the materials were very different. They were traditional materials, lime mortars, lime plasters. They allowed moisture to move around the building in a very different way to modern buildings. And modern buildings, very different. So we don't heat with fires, we heat with central heating. We expect the whole house to be a nice even temperature all the way around. We no longer have single glazed windows, we have double glazed, triple glazed in retrofit houses and more modern houses. And we've done a lot of draft proofing, especially through the 80s and 90s and early 2000s, loads of draft proofing done because we realized we do not like drafts. And what it doesn't say on here is the materials that we use now, more modern building materials, these are not breathable. Your gypsums, your concretes, your cements, they do not allow moisture to move in the same way. We are changing the mechanics of the buildings. So I'm going to now do a knowledge check. I'm going to do a couple of these as we go through. What I'd like to do is I'm going to ask you a question and I'd like you to put your answer into the chat, but don't hit enter yet. I want everybody to have a go, give me an answer, and then when I say go, everybody hit enter, and then I'll be able to see what's going on. So let me be able to see the chat. And your first question is, just to check you've been listening, what does it mean to take a whole house approach? Give you a little minute, and then you can give me an answer, because I'll also have a quick drink. Okay, if you've typed something in, hit enter now. See what we say. And the fabric of the building, house and system, looking at all the interaction systems. Yes, viewing the whole house and system fabric first. Excellent. There's people in the room and they're listening. Marvelous. Okay, you all pass. Let's talk about how heat moves around our homes. I'm sorry, Tina, I realized I didn't take a note of what time we started. What time did we start, just so I don't get too excited and talk about any one thing for too long?
Don't worry, that's fine. And we started a bit late, so I think if we carry on till about 8, if that gives you enough time, but if you run over slightly, don't worry.
That should be okay. I might need to go a little bit quicker through some bits, but that's fine. Okay, heat. Talking about how do we lose heat from our buildings? So these are some graphics from the Home Energy Planner report that is an assessment tool designed by People Powered Retrofit, which it's the tool is used by CAFs to do energy assessments around Cumbria. What this basically shows you is, of all the different bits of the building, where's losing the most heat, so you can really get an idea of how you may best target your retrofit interventions. And the idea is that you look to reduce heat loss from as many of those places as possible. This looks at both fabric losses and ventilation losses. So there are losses on here for planned ventilation, and there are losses on here from drafts. Drafts and ventilation are two very different things, which we will come on to later. It's not just about heat loss, though. We're always trying to balance the losses against the gains. What are the gains? Gains come from lots of different places. So we get heat gains from us. Every person that's in your house is emitting, in general, about 100 watts in heat just by being there. Your pets will also be emitting heat. It will depend on your activity as to sometimes you'll be emitting more heat, less heat, depends what you're doing. We get gains from cooking. If you're doing something that is anything that's creating heat in your house, either intentionally or unintentionally. So when you're cooking, when you are on your laptop watching a webinar like this, your laptop, your computer is going to be emitting heat as well. And we also get solar gains. So when the sun is coming in through our windows, we're getting some of that heat into the house as well. And we balance these. This is another graph from these from the Home Energy Planner reports. What we see are everything above the line is a gain, everything below the line is a loss. So the yellow is the fabric losses, the greeny blue are the ventilation and infiltration losses. Then we get a bit of a gain. The big gains at the top, that's the space heating requirement. So that's how we need to balance the losses and the gains to get a nice stable temperature. So space heating demand is a really important metric here. It helps us to understand how different buildings perform against each other and what is realistic. So the UK average is about 140 kilowatt hours per meter squared, kilowatt hours being the amount of energy you need to put in. A kilowatt hour is what you'll see on your energy bills. And so it's kilowatt hours per meter square of the floor of their building per annum. That's the point A. Buildings regs has a target energy efficiency rate of about 100 kilowatt hours. It was in 2000, and that's gradually coming down to about 65. And then there are various standards you can look to, like what is a good heat loss, a good space heating demand to aim for. So the AECB, that's the Association for Environmentally Conscious Buildings, a very good organisation. I recommend looking them up. They have a retrofit standard. Their retrofit standard aims for 50 kilowatt hours per metre squared per annum. That's the retrofit target, I think. And they have a new build target, which I think is the 40. And then we have Enefit, which is the passive house standard for retrofits. And that's 20 to 30 kilowatt hours. And then passive house, which is the standard for new builds, but that's basically the super low target. It's 15 kilowatt hours per meter squared per annum. That's tiny compared to the UK average of 140. I delivered some training up in Aberdeen last year, where their average up there is sort of 250, 300. Wouldn't surprise me if you very similar average for Cumbria when we're thinking about it's that bit colder, it's that bit wetter, and it's a different type of buildings. In Aberdeen, it's lots of granite build. I know in Cumbria you have a lot of stone buildings, so you will often have a lot higher space heating demand. Lots of things play into it, not just what the building's made of, but also what we call the form factor. This is just it's a ratio between the floor area and the external wall area. The more external heat loss area you've got, the worse your form factor is, the less efficient it is. Essentially, if you're if you've got a flat that's in the very middle of a building and the only external wall you've got is on the front where your windows are, you've got a lot less surface area to be losing heat from than if you're in a detached bungalow. That's what this is saying about. You can choose your form factor when you're building a house. There's not a lot you can do about it with a retrofit, but you can think about it if your retrofit also includes some construction work. For example, if you're looking at doing an extension or a conversion, you might be able to tweak that to try and improve your form factor as you go, which will reduce your heat loss area. Other things that we might look at, peak heating demand. This is the rate of heat input you need. So on the coldest day, how much heat you need to put in. It's not that interesting by in and of itself. What it's basically looking at is for sizing your heating system. We want to try and make our peak heating demand as it basically falls into bands, especially when you're looking at whether you can switch to a heat pump, for example. This is very much when you're sizing heating systems. What's possible in retrofit? So this graph is about, so this is showing you a few different things. What's the bottom? This is, they looked, Carbon Co-op looked at, Carbon Co-op, by the way, the parent organisation of People Powered Retrofit. They looked at 5 different houses that had been retrofitted. They looked at modelled and actual data before and after the retrofit. So this is showing that there can be a real difference between what you model and what is real. Important thing to remember is that all models are wrong. Some of them are useful, but they're all fundamentally wrong. But you can see here we can get really significant reductions in space heating demand by doing a really good job of a retrofit. But this is something that graph showed there was a difference between modelled and actual results. This is very important post retrofit because unless you're very careful, you can end up not reaching your goals because of the performance gap. Now, what this basically is describing that difference between what you modeled and what you actually got. And there are a few reasons why we get this performance gap. But it's very often to do with assumptions that are made at the beginning that aren't necessarily close enough to reality. Attention to detail in design, quality control during construction. This is really important. You can put as much energy as you like into designing the perfect retrofit, but if what you have designed is not what is installed, you will have a performance gap. If you have designed for a really high level of air tightness, but your contractors don't understand how to install to that level of air tightness, you will not hit your targets. So it's really important that what is designed is what is installed. Making sure, like, suitable commissioning and handover, making sure that what is installed works the way that it's supposed to, and making sure that the householder knows how to use it. All very well and good putting in a very expensive heating and ventilation system. If the client doesn't know how to use it and turns it off, it's not going to work. You're not going to hit your targets. And if you don't maintain what's there, you're also not going to hit your targets. If you don't change your filters in your fancy MVHR ventilation system, then it's not going to work as intended. And here we go. This is showing these error bars, the difference we can get. That performance gap can cause a really big fluctuation in performance. So I'm going to do another one of these knowledge checks. What does space heating demand mean? If I'm talking about space heating demand, what is that? Answers in the chat, please. Okay, hit enter if you've typed something in. Let's see what you got. How much energy it takes to keep the house comfortable. Perfect. That's exactly it. How much energy do we need to put in to keep a nice, stable, comfortable temperature? Okay. So I'm going to do a bit about heating. So heating level is everybody has a preference how where they set the thermostat. We used to have battles in our house whether was it going to be 19, was it going to be 17? We now settle on about 17 and a half. There's a lot of research that's gone into this. What is actually a sensible temperature? Want to advise people it should be ideally above 18 degrees for most of your house, slightly cooler in your bedrooms because we sleep better in a cooler room, but we don't want to go too cold. Under 16 degrees can really start to cause us some health problems, but it can also really cause problems with the fabric of your building as well. The colder your building fabric is, the more likely you are to get damp and mold. But it's also really important for human beings to be warm enough. But the way that we perceive warmth is quite, I find it very interesting. There's a lot of people who find it very interesting, but I think it's really important to understand the way that we perceive warmth and how comfortable we are. It's very individual, but it's also affected by lots of different things. So the way that we measure temperature is generally air temperature. That's what a thermometer is often picking up. But I want to show the difference between these two locations. Okay, so we've got someone standing in a sunny but windy area and someone standing in a shady but calm area. The air temperature in both locations is 22 degrees. The relative humidity in both locations is 80%, but the wind speed is different, and the radiated heat is very different. So these people are going to feel it's going to feel very, very different temperature wise in these two locations. Different people perceive heat slightly differently. But I just want to say that it's not strictly the temperature. It's got lots of other factors involved. What does that mean in our houses? Well, let's come on to that. So when you do physics at school, they tend to teach you different ways that heat is transferred. There are four main ways: conduction, convection, radiation, and latent heat or sensible heat. I'm going to concentrate on this for conduction and radiation. Conduction being about how is the heat transfer mechanism through a solid. So this is the way I was explaining this. If you stick your spoon, your metal teaspoon, in a hot cup of tea, the heat will move along that spoon to the end and will eventually warm up. It's all about vibrations, particles vibrating next to each other and passing the heat along. This is how heat moves through the physical fabric of the building. And we're going to talk about radiation, radiative heat, specifically in terms of surface temperatures, how we perceive temperatures around us. So this is an image from a thermal imaging camera. When we talk about temperature, we're normally talking about air temperature, but this is really important. This is showing us the radiated temperatures around us. This is showing us how different surfaces are different temperatures. Everything that's above absolute zero is radiating heat in quite small amounts, but everything above absolute zero is radiating some heat. We can see from here that the warmest areas in this image are about 14.3 degrees. The coldest is down to one or 2 degrees, but it's all radiating some kind of heat. This doesn't tell us anything about what the air temperature is. This is just what these surfaces are at. What does that mean in our houses? Well, again, obviously the faces on these are a little bit disturbing. But this is basically showing the difference between sitting next to a double glazed window and a triple glazed window. When we're sitting next to a cold surface, we feel cold. So if we're in a room, or what this is saying is on the left-hand side, the room temperature is 21 degrees and outside is minus 14 degrees. That is cold. But what we're looking at is what is the temperature on the inside pane of that glass. On the double glazing, the inside pane of glass is about 15 degrees, this is telling us. Whereas with the triple glazing, it's 18 degrees. The key number to remember here is if there's a difference of about 4 degrees, you'll notice it. You will feel cold sitting next to that window. This is why it's quite nice to have some nice warm curtains. If you just close the curtains there, the air temperature in most of your room hasn't changed, but you're no longer sitting right next to a really cold surface. Yeah, we feel it's this radiated heat that we humans are very we're very sensitive to. If you think in really warm countries across the Middle East, for example, you will often have large pools of water because they help you feel cooler, because the surface temperature of the water is a lot cooler than everything that's around you. The air temperature hasn't really changed, but there's a much cooler surface. And you'll feel cooler. So how do we improve comfort? Well, the answer to this is insulation, and it does this in two ways. So adding insulation to the building fabric reduces the heat loss via conduction through the fabric because it slows the heat transfer. But it also raises the surface temperatures inside. So whether you're insulating internally or externally, the internal face of that wall is going to be a lot warmer. So you won't have that cold surface making you feel colder. Sorry, I'm just checking the notes on it just to make sure. Yeah, so it doesn't affect the conduction and the radiation temperature to the same degree. It's much more about slowing the heat through, but you will notice if a wall previously had been particularly cold, it will feel warmer once it's been insulated. Here's some examples of some internal and external wall insulation. This one on the left, that's internal wall insulation, which is mineral wool internally between timber battens. Top right, that's wood fibre insulation internally, and bottom right, that is wood fibre externally. It doesn't matter where you put it, as long as it's there, it's going to slow the heat loss through that wall and warm up that internal surface. But it's not just about staying warm in the winter, it's also about staying cool in the summer. If we've got insulation on that wall, it's going to slow the heat coming in the really warm summers. I know we've had some really scorching summers over the last few years. Not this year. This summer was certainly was a bit of a washout in Manchester. I don't know about in Cumbria, but we have had some warm summers recently. We can think about the position and the amount of windows and glass if we get an opportunity to change that, so we're not getting that solar gain. We can add shading, but we can also choose materials that slow down the heat coming in. Especially a really key place to think about this is in a loft conversion. Some materials you might use in a loft conversion are good for retaining the heat in the winter, but they are not very good at keeping excess heat out in the summer. I go into a lot of really scorching loft conversions in the summer. And we can also address heat through really good ventilation. So heat and air, right? I'm going to have to speed up, so bear with me. Convection is one of the other types of heat transfer that we didn't talk about. Convection is the movement of air. This is where warm air, we get more gap between the particles, makes it more buoyant. Warm air rises, then it cools and falls, and we end up with these convection currents. Convection heat loss is really important because we lose heat through various mechanisms. Thermal bypass, chimney effects, drafts, and ventilation. I'll go into each of these. So thermal bypass. Thermal bypass is a little bit complicated, but essentially what this is about gaps and air movement around insulation. It's about air movement stealing the stored heat from your insulation. Sometimes it's called wind washing. But this is why we will often cover insulation with a membrane if it's not being covered over with plaster, for example, under a floor or in a loft. It's also really important that we have insulation really well installed so that there aren't gaps for air to get in and remove the heat. Chimney effects. I think most people are quite comfortable with this idea that we lose. Chimneys are designed to draw air up them so that we don't fill our houses with smoke. They do this because warm air is more buoyant. If we're not very careful, we can end up with a chimney effect through cavity walls where we have warm air from our homes gets into the cavity wall. It then rises up, sucks more cold air in from the bottom, and we end up with this cycle of losing our warmed air up the cavity wall. If we cap cavity walls off at the top, then we end up with a convection current through them, but hopefully we are gaining that warmth back into the house rather than losing it straight out the top like it's going out of a chimney. I said earlier that drafts and ventilation are two very different things. They are. So on the right, ventilation is planned. This is about providing fresh air into our homes and extracting moist air, removing water vapor and pollutants. Infiltration is drafts. This is air that's coming into our homes. Sorry, air that's coming out, well, in and out. So it goes both directions. Where we lose our warmth, but we also get cold drafts through our homes. This is unplanned. We don't want this. This is why we do a lot of draft proofing. And this is where air tightness is really important. If we have a house with a really low level of air tightness, so lots of infiltration, lots of drafts moving around, we get what these diagrams term energy leakage. So this is warm air that you've paid to heat up escaping through gaps. You end up with higher energy bills, higher emissions, and it's pretty uncomfortable living in a really drafty house. We don't like that, and we get degradation of the structure because we end up with moisture moving around. We don't want that. In a house with high levels of air tightness, we're really making sure that we're keeping that heat in, not just through a really well insulated structure, but we're keeping those drafts out. We're controlling where the air is going out, so where our extracts are, and where our air is coming in. I always say I don't really want to be breathing air that comes from under my floor in my loft. I want nice, fresh outside air. And we can also really make sure that any system is working really well if we've got good air tightness. We can measure the leakiness of our buildings. We do this through air tightness testing. This is Gervais, who's an air tightness specialist doing a blower door test. You have some really good people doing air tightness up in Cumbria. I think Diane Hubbard is probably doing some of these webinars. She's fantastic. She's green. Her company is Green Footsteps. She does air tightness testing. Essentially, what you do is you put one of these. It's called a blower door test. You put this in your door. It's got a big fan. It sucks or blows air in or out of your home, so it's forcing air in or out through all the little cracks and gaps. You can measure how much air is being lost. There are lots of targets because we can quantify it. So the average, the metric is called air permeability. This is how leaky is your house. Low numbers are good. It means it's less leaky. The average house is between 12 and 20. Won't worry about the units, it's very complicated. Buildings regulations, this needs updating actually. It used to be 10, it's now 8. Good practice would be 5. And right down the bottom of here, passive house. On a passive house, you're not allowed to have an air leakage of more than 1. So if you compare that, what the average is between 12 and 20 and what a passive house is of 1, our houses are ridiculously leaky. Older houses were designed to be leaky because they had fires in. We needed the fresh air. But now, as we've tightened everything up and we're doing lots of air tightness works, we should be getting down to these really good tiny numbers in here. How do we do it? There's lots of things you can do to improve your air tightness. This one here is filling the gaps between floorboards. Ideally, you want to deal with air tightness and insulation at the same time underneath your floor if you've got a suspended timber floor. But if you can't do that, fill the gaps between your floorboards. The bottom left, this is some pretty serious air tightness works. This is taping. This has got a membrane and tape going around, possibly a joist, I think. And then we've got some examples on the right of this is somebody looking at taping and membranes, and there's going around pipe work and other penetrations, so pipes, wires, all these kinds of things. I think what's important to take from this is air tightness is really important. There are lots of products and methods available. Your air tightness strategy should be part of your whole house plan. It can really make a difference. If you do nothing about the air leakage from your house, you're missing a massive part of the heat loss. And you will not hit your targets if you don't also deal with air tightness. So, knowledge check. What's the difference between infiltration and ventilation? Are we still here? I've got go for it, put your answers in the box. Ventilation is planned. Absolutely. Unplanned versus planned. That is exactly it. That is exactly it. Ventilation, good. Infiltration, bad. Lovely. Okay, moisture. This is really important. So if we think about heat, but we don't think about moisture, we are going to have these unintended consequences that I spoke about at the beginning. Most of the unintended consequences of retrofit are to do with moisture. Moisture is not something we want getting into the fabric of our buildings. Damp, mold, degrading structure, all bad things. We can plan to avoid issues with moisture, and we definitely should be doing. So moisture flows interact with and are affected by heat. What does that mean? Well, if we think about the different ways that heat move, if we're thinking about air movement, thinking about ventilation, infiltration, moisture is in the air and will get moved around with air as the air moves around our homes, but also moisture moves in and out of the building fabric as it was supposed to in traditional buildings, but it can't so easily on newer buildings. So I'm not going to play this video, but I recommend you look it up. I'm sure that CAFs probably have this in multiple places on their website, and they will point you to this. It's a fantastic video by the UK Centre for Moisture in Buildings. It talks about what are all the sources of moisture in our homes and what are the effects and what can we do to manage moisture. There's various things. There's moisture from outside the home, there's moisture from inside the home, and it also explains relative humidity. What is it? Why is it so important? I won't go into it now because I'm tight for time. Go and have a look at this video. It's really I use it in all the presentations that I do about moisture. So moisture on the building fabric. When moisture gets into the building fabric, well, I think most people have dealt with this at some point. So this is what happens when we have lots of moisture in the air inside our buildings, and we've got a cold bit of building fabric. We all know that if you go up to a piece of glass and breathe on it, we get condensation on the glass. The exact same thing is happening, condensation on every surface in your home if it is cold. And it doesn't have to be super cold. It just needs to be about 5 degrees colder than the air in the room. So if you're heating, if your internal air is about 20 degrees, if there is a surface in your home that is about 15 degrees, you are very likely to get condensation. If you have enough condensation on that wall, you will get mold, this black mold that so many of us are so familiar with. It's very frustrating. This is a quote that gets used all the time. Any retrofit project that does not consider ventilation is a condensation project. We deal with this excess moisture in the air and our internal air. It's not excess, it's nothing you're doing wrong. Just by being a human being inside a building, you are producing moisture. We breathe moisture out. We like to, as humans, we like to breathe, we like to wash, we like to cook. All these things create moisture. How do we deal with the moisture? Through good ventilation. What these images are showing you is how the fabric of the building was designed to deal with moisture. On the left-hand side, we've got a standard solid brick wall. Moisture was able to pass through these old bricks. Moisture can pass through them. Lime mortar, moisture can pass through. As soon as you start putting modern insulation, impermeable insulation on them, you trap the moisture inside that wall and it can't get out. Which is why you should use the correct insulation for your wall, which if it's a solid wall will need to be, call it a breathing insulation. I wouldn't use that term. I would use a vapor permeable insulation material, something natural or breathable. When we say breathable, we're not talking about air, we're talking about moisture. It's the wrong word, really. It's a construction, a building can be airtight and breathable, all to do with the size of molecules. If you're interested in the science, I find it very interesting. Go and read about it. There are various mechanisms that we talk about moisture in buildings. You may hear these terms: vapor permeability, hygroscopicity, capillarity. It's various ways that moisture can move around buildings. As householders, you don't really need to know the science of these things. You can go and read about it if you want to. What you need to understand is that your retrofit project must consider how moisture currently moves around your building and how it will, how your retrofit project products measures may affect that and how moisture is going to be managed afterwards. The ventilation should always be part of your retrofit project to be able to manage the amount of moisture that is in the air. The material choices can be really important as well. Ventilation. There are lots of ventilation systems available. I'm not going to go into all of the different ones. Suffice to say, buildings regs only really allows you 2 different types of ventilation systems these days. That is continuous mechanical extract ventilation. That is fans that are running constantly to deal with the general background ventilation because you're in your house breathing all the time. And then there will be boosts on the fans in your kitchen and bathroom for when you're doing something that is particularly adds a particularly high moisture load, usually washing, cooking, those kinds of things. And then the top of the line would be an MVHR, that's mechanical ventilation with heat recovery. Again, that's a whole house system that deals with constantly running fan, background ventilation all the time, and fans that boost. But an MVHR system also deals with supply air as well. You have a lot of ductwork around the building, so you've got ductwork going extract and inlets, and then there's a heat exchanger, so you recover some of the heat from that air before it leaves, and they can be extremely efficient if well installed. They also have filters on the air, so you get really beautiful air quality on an MVHR system. I wouldn't recommend any other types if it's not continuous extract. It's almost definitely not doing enough ventilation for your building. Talk to somebody who understands it. Diane Hubbard knows an awful lot about it. Tina knows an awful lot about it. Everybody who does the assessments for CAFT know a lot about ventilation. Speak to someone about it. You definitely need more ventilation than you currently have in your home. I made it to the end. Okay, not too far over, I hope. Um, hopefully I'm not in too much trouble. Okay, so to wrap up, it's been a bit of a whirlwind through retrofit. So a whole house approach is needed. A house is a system. Well, it's lots of overlapping systems interacting with each other. We've got fabric heat loss, we've got ventilation, heating, lighting and appliances, and then tricksy people. All of these things interact, making it quite complicated, but manageable to deal with these things. That can't be all I've told you. I've told you other things. When we do a retrofit project, we need to think about all these systems. And generally our approach should be fabric first. We want to reduce the heat loss through the fabric to keep the heat inside the building. We want to think about airtightness as part of our reducing heat loss, and we need to think about ventilation so that once we've done some really good airtightness work, we're then supplying air and managing any moisture that is being created. There, we made it to the end. Did we have any questions that came up
Thank you
as I
so
went?
much. Thank you so much, Marion. Yes,
No
it's a
problem.
big topic, and you've
Huge.
given a brilliant introduction. So we do indeed have some questions. I can see a couple in the chat, and if anybody else wants to put
Wonderful.
questions in the chat or the Q&A, that would be great. So one person has asked about what about single room MVHR? Well, yeah, single room heat recovery units.
I haven't had much experience of we haven't had any projects that use them. I've had them explained to me a lot. Um, you can have a whole house system that works with individual units. You need to think about it as a system for the entire house because all your rooms are connected. Rooms don't operate in isolation. Um, I would want a system that has been designed properly. If it's going to be, well, any system should be designed properly by somebody who really understands it. It may or may not consist of individual units in lots of different places. One through the wall fan with heat recovery does not make a ventilation system, I think is the answer to that.
I suppose sometimes people are just replacing an old extract fan in a bathroom. Now,
Mm.
the extract fan would have dragged cold air through wherever in the house it could get in, and it would have extracted it and thrown it out through the hole in the bathroom wall. So that has some merits in that it's drawing heat through your whole house, or drawing air out of your house. But it would also be taking the heat out with it. If you have an extract fan just in your bathroom, sorry, a heat recovery fan in the bathroom, that is exchanging the air and keeping some of the heat in the bathroom. But what about the rest of the house? So I think there are pros and cons, and it probably depends on what level of work you're doing. If you're doing a sort of temporary measure for the bathroom now,
Yeah,
okay. But if you're planning a big retrofit, do it properly, basically, I think is the
yeah,
main thing. Yeah.
absolutely. You will need more than that one fan in the in the bathroom. But yeah, if it's as part of a phased retrofit, then maybe I would want to take advice from people who live and breathe ventilation systems are the ones to speak to about that.
And we've got another question about trickle vents. So what about trickle vents in windows for ventilation?
Okay, so a trickle vent will not provide ventilation in and of itself, um, but it can be an inlet as part of a ventilation system. So if you have, for example, a continuous mechanical extract system, so your fan generally, so if you have a centralized system for that, I think it's the easiest one to think about is you have one big fan that is extracting from all the wet rooms in your house. Bathrooms are very often on top of kitchens, so it actually makes sense in these. So one fan extracting the moist air from those rooms. Houses are not vacuums. You need to add air back in, and the air will often come back in through trickle vents. You're choosing that is the place I'm going to bring air in. Trickle vents do not let are not reliable for letting moist air out. They don't do that, therefore letting air come into your house to make up for the air that's being extracted from elsewhere. If they are part of your ventilation system, they should be left open. I know they can cause drafts and make you cold, but they're there for a reason. They should be open. But you would generally not have them if you're, say, for example, you're going to an MVHR system. You would not want trickle vents in your windows. It can take a little while to sit and look around your house and work out, what is my actual ventilation system? How do all these things actually fit together? It's worth having a look around and work out, where is the air being extracted from and where is the air coming back in from, and try and join those dots. They should be being extracted from wet rooms and coming into the living rooms, so lounges, bedrooms, those kind of places.
Yeah, brilliant. So yeah, I mean, it's looking at everything all together holistically, which is, I think, really important, and what this talk is about, thinking about everything. And what I would say is a quick plug for our air tightness webinar next week, the insulation one the week after, and the ventilation one the week after that. So our next question, and we haven't got much time for questions, so I might suggest this is one about cavity walls, that we've been told that the southwest facing walls are too exposed to wind and rain to have cavity wall insulation. And just wanting, very briefly, could you say why? And perhaps we'll say more about that in the insulation webinar itself.
Yeah, so this is about this is a moisture issue. So especially for Cumbria, this is your walls have cavities in. The external leaf is about being weatherproof, and the internal leaf is to keep you warm. And you add insulation in between the two to really beef up the insulation value. However, if you've got something in that gap, you can end up with moisture traveling from the weatherproof side to the internal side. And a lot of the insulation materials that you would use for cavity wall insulation can really bridge that gap. If you are in a really exposed location where you get the horizontal rain, your weatherproof layer has to do an awful lot of work. And if you get moisture into that cavity, it's an absolute nightmare, because that moisture is only going to come straight into your house. It cannot get out. It's coming in, which is why you've probably been told you can't use it. There are ways around this. It doesn't mean all cavity wall insulation is bad. It just means in some places it's riskier than others. Speak to someone who really understands this, like CAFs.
Yeah, and talk to other people. I mean, I've got one wall where that has happened. The cavity wall insulation got wet and it had to be all sucked out again. So, it can be taken out, but it has to then take 6 months to dry. So, it's inconvenient, and it's best to get proper advice on that one. I think this will be we've got a couple more questions, so we'll need to be quick with these. How possible is it to be successful with a house that is part new build and part slate stone? The house was badly damaged by a tree fall, and half needs to be rebuilt, but half is still the original slate stone.
It is very possible to have really good outcomes. What it's going to take is good planning. So you need to make sure that you really understand what you've got. So really good assessment at the beginning to work out which bit of the house is constructed in which way and how these different types interact, and then a really solid design process for your retrofit to really understand how to deal with each different bit of the fabric. You will need different approaches in different places. And where those construction types join, you will need some thought about the interaction. But I've seen projects with really great outcomes on houses that have very different construction types around them. It's pretty common. It's pretty common to have a solid built main house, and then you've had an extension put on at any point since the house was built. None of our houses are as built, so we're always dealing with something that's changed over time. Does not exclude you from anything, means you just need to be a little bit more thoughtful as you go into the project.
Yeah, and get relevant advice, particularly for that scale of project. You're talking about an architect anyway So get an architect and try and get someone with retrofit expertise, or get some retrofit consultant. Another question here: I live in a stone-built house and get lots of condensation on the cold wall below my bay window. Can I put some insulation on the inside on that small area, and what could that be?
Ooh, okay. Now, this can be
Or is
tricky.
this one for the insulation webinar where we've got more time to focus on a tricky
Yeah,
one like that?
this is something to really understand what's going on, because it could be several things all playing in together. Bay windows are often, it's really hard to predict how that bay window has been constructed. Sometimes it might look like it's brick or stone from the outside, but actually it's not brick or stone all the way through. It could be timber with something stuck on the front of it. There is no hard and fast rule. I think I'm going to say you need to speak to somebody who can come do an assessment and really work out what it is. But I know that the home retrofit planner tool, and the people who come out and do it, they will be looking for these things. You can have the conversation beforehand. They want to know what are the target the areas that are of particular concern. They can come and really investigate what's going on. I won't want to say it's one thing or another without seeing it.
Thanks, Marion. Well, I think that's all the questions we've got time for, because we started a bit late. So what I'd like to do now, I'll just sort of wrap up by share my screen there and see if it will. Can you see those at the moment? Is that showing nicely now? Okay, so if you've got other questions that come to your mind, it will probably be covered in our forthcoming webinars. So do come along to one of those and bring your questions. So that's air tightness, insulation and ventilation. You can also phone CAFS for a short advice call with either our Cold to Cozy Homes team, or if you're wanting a retrofit consultation because you think of something a bit, you're looking at the whole house, then you can contact our retrofit team there, and you can apply online via our website. The future webinars, as I say, every Thursday for the next 3 weeks, and you can book on at CAFS Org and Events. You can sign up to our newsletter, and you can join the Facebook group Cumbria Greenbuild, where you can communicate and share information around with each other. We'd love to hear from you if you've got questions to ask from our advice that we can offer at CAFS. And also just to mention our new shop at CAFS, where we've got Christmas gift cards where you can support different projects that CAFS is running. So thank you for attending. Thank you for your questions. Thank you for anyone who's made a donation, and a special thank you to Marion, who's given such an interesting talk and covered a big topic, really in quite a bit of detail in a relatively small amount of time. And thank you everyone for attending, and hopefully see you next week.